All right, last video. This should only take 5 minutes or so. We're going to talk about Bernoulli's equation for a minute. And Bernoulli's equation is just the conservation of energy under ideal reversible type of circumstances. So in other words, no losses, no heat transfer, basically no viscosity causing these losses in heat transfer. It's called inviscid, and also no shaft work. So if we take out those HF and HS terms, again, one inlet and one exit, P1 over rho G plus V1 squared over 2G plus Z1 equals P2 over rho G plus V2 squared over 2G plus Z2. And now we don't have any other HFs and HSs added on here, so basically this whole term that contains a certain head energy at position 1 has to equal that same term at position 2. We can just say that that is equal to a constant. We usually use this equation for external flow. In other words, wings, flow over your cylinder, that kind of thing is what we usually use for it. Also, if it turns out that it's flow over wing or whatever, we're not changing the elevation between point 1 and point 2 very much, we're going to be able to cancel out our Z1s and Z2s, and we get P1 over rho G plus V1 squared over 2G is about equal to P2 over rho G plus V2 squared over 2G. And this should look a little bit familiar to you if you're in the lab, because that is where we got our pitot probe equation. Came from that. So we said that V1 was out in front of the probe, or had to do with the pressure right on the side. And V2 was equal to 0 because it was the stagnation pressure right there at the front. And we were able to solve then for V1, so the pitot probe velocity equation. Again, usually for qualitative analysis, because it doesn't include those losses. And there really are losses, okay? So it's kind of the idealized situation. That's also where our CP for the ideal flow around a cylinder came from. So what we'll do is, let's say we have a wing, and we have flow over a wing. Our 1 we want to be, say, upstream, okay? So 1 is normally along a streamline, somewhere upstream, outer flow, and usually that's all the same. So if you have an airplane flowing into still air, it's the same as an airplane with air flowing over it, so it'd be out in front, kind of like where we measured our pressures on the side of the wind tunnel. So let's take 1 to 2 as 2 being up here. Okay, and what we'll see if we do that is that we have a higher velocity here, okay, at 2 than we had at 1. So that means if this has to stay constant, then if our velocity goes up, well, our pressure has to go down. That's where we're talking about, that's where this comes from, talking about the inverse relationship between velocity and pressure. If we look at the bottom, so we say 1 to 3 instead of 1 to 2 up here, same thing. If the velocity is lower, then we must have a higher P. Okay, so if, in other words, call this 3, if V2 is greater than V3, then P2 must be less than P3, and from that we can see we've got lift, because we got a higher pressure pushing on here, lower pressure pulling up. That's where the lift comes from. All right, wow, this is messed up, isn't it? Basically it says a key to these conservation of energy problems again. So that was it on Bernoulli's. So now I'm just talking conservation of energy in general. A key again is to draw your control volume so that everything is as easy as possible. So you get a lot of zeros or V1 equals V2 and that kind of thing, and you can cancel things out. So that's what you want to do. So, and these are kind of the keys, the things you want to look at. Do you have a free surface? If you do, make that your inlet or exit, okay? If you have a constant mass flow rate and incompressible fluid, which we're always going to have incompressible fluid, then if the areas are same, your velocities are going to be the same, and then you can cancel those. Horizontal, V1 equals V2. If not, if you do have an elevation change, draw your coordinate system so that Z1 or Z2, one of those is 0. That also helps. If there's no pump or turbine, HS will cancel. If you're trying to find something with the pump and turbine, make sure that the pump or turbine is between your inlet and your exit. And also remember that pressure at a jet exit where it meets the air is going to be just P atmosphere, and we're always going to be using gauge. I should write that, use gauge pressure. Because just like the forces cancel from atmospheric pressure everywhere, so does the energy. Okay, and you can go ahead and finish the quiz. That's what this says, is finish the quiz. And also note that the next page, which is not showing up here because this is all messed up, is a summary of all your control volume analysis equations. Okay.